Bismillah ar-Rahman ar-Rahim. The topic of this video is the generating function of the binomial coefficient 3n choose n. We are interested in this sum, n from 0 to infinity, 3n choose n, x to the n. We obtain this sum using this integral here. To represent the sum using the integral, we also need to represent the binomial coefficient using the beta function. For this, we employ the multiplication formula. Let's derive it. Starting from the limit definition of the gamma function, gamma of x is limit as k tends to infinity, k factorial k to the x minus 1 divided by this product, x plus 1, all the way to x plus k minus 1. We use Stirling's result, the ratio of k factorial to the square root of 2 pi k, k to the k, e to the minus k, tends to 1 as k tends to infinity. We replace the factorial of k here by this quantity, replace x on both sides by z plus m over n. N is a positive integer, m is an integer from the set 0, 1, 2, all the way to n minus 1. Multiply upstairs and downstairs by n to the k. We can split this to the square root of k, k to the k, and then we can join this term here to have kn all to the power k. In the denominator, we have k terms in this product. Multiply each term by n. We get the product g from 0 to k minus 1, nz plus m plus gn. Take the product of both sides over m from 0 to n minus 1. Note that those limits are finite so long as the value of z does not give us 0 in the denominator. The limit of the product is the product of limits, so long as we have a finite number of terms and each limit is finite. On the right hand side, when the product is applied to k to the m over n, we are summing over m from 0 to n minus 1. The sum is equal to 1/2 n minus 1 times n. After dividing by this n, we get k to the n over 2 minus 1/2. Let's investigate the product in the denominator. We have a product over m from 0 to n minus 1, g from 0 to k minus 1. Here we have nz, and we have m plus gn. Let's investigate this part here as m and g take their respective values. If g is equal to 0, m plus gn is equal to m, and m goes from 0 to n minus 1. If g is equal to 1, we have m plus n. M is in the range from 0 to n minus 1, so m plus n is in the range from n to 2n minus 1. If g is equal to 2, m plus gn is m plus 2n, which sweeps through the integer values from 2n to 3n minus 1, and so forth. M plus gn is an integer that starts from 0 all the way to kn minus 1. This value is achieved when m is equal to small n minus 1 and g is equal to k minus 1. We can write the denominator as one product g from 0 to kn minus 1 of nz plus g. Finally, we have this product. Note that there is no m here. So this product simply means that we take this quantity and raise it to the power n, which is the number of terms in the product. We get 2 pi to the n over 2, k to the n over 2, kn to the power kn, e to the minus kn. We also have k to the nz minus n. Split this n over 2 to 1/2 and n over 2 minus 1/2. We have this term and that term. Together they give us k to the n minus 1/2 times k to the nz minus n. Separate the square root of k. We are left with k to the power nz minus 1. The objective now is to make this limit look like a gamma function. We started with gamma of x equal to the limit as k tends to infinity, the square root of 2 pi k to the k plus 1/2, e to the minus k, k to the x minus 1, divided by the product g from 0 to k minus 1, x plus j. Compare this with what we have. Downstairs we have nz in place of x. This motivates us to try to write down this limit as gamma of nz. In this definition, the number of terms here is k, and k is the variable with respect to which we are taking the limit. But here we have kn. Note that n is a finite positive constant. If k tends to infinity, then kn also tends to infinity. To be able to write down this as gamma of nz, we need kn to be raised to the power nz minus 1. But we just have k to the nz minus 1. So we multiply by n to the nz minus 1, and outside we have n to the 1 minus nz. In the limit definition, we have the square root of k. Now k is replaced by kn, so we need the square root of kn. We multiply this by n to the power 1 over 2, and outside we multiply by n to the minus 1 over 2. The combined effect is that we multiply outside by n to the power 1/2 minus nz. We get the square root of kn, and we get kn raised to the power nz minus 1. If the variable of the limit is k, we have e to the minus k. Now it is kn, and we have e to the minus kn. So after doing this adjustment, this limit becomes gamma of nz. We have the outside factors, 2 pi to the n minus 1 over 2, and n to the power 1/2 minus nz. This is the multiplication formula. We can rewrite it as gamma of nz equal to n to the nz minus 1/2, 2 pi to the power 1 minus n over 2, then the product, m from 0 to n minus 1, gamma of z plus m over n. What we need for our task is the special case when small n is equal to 3. Gamma 3 of z is equal to 3 to the power 3z minus 1/2. If n is equal to 3, we have 1 minus 3 over 2, that's minus 1. So we have 1 over 2 pi. The product has 3 terms. Small m is 0 or 1 or 2. We get the product of gamma of z plus 1/3, gamma of z plus 2/3. In our task, we have the binomial coefficient 3s choose s. The numerator has the factorial of 3s, which is gamma of 3s plus 1, which is 3s times gamma of 3s. Now we have a formula for this term here. To obtain the generating function, we make use of this integral. To evaluate this integral, let's start with this sum, n from 1 to infinity, minus 1 to the n plus 1, x to the n sine n eta. X is a real number between minus 1 and 1, and eta is a real number between minus pi and pi. Sine n eta is the imaginary part of e to the I eta n. We can split this into minus 1 times minus 1 to the power n. The sum is equal to minus the imaginary part of the summation n from 1 to infinity minus x e to the I eta, all raised to the power n. Because x is strictly less than 1 in absolute value, the magnitude here is strictly less than 1. We have a convergent geometric series. We get the ratio times minus 1, so this is x e to the I eta. Downstairs we have 1 minus the ratio. This is 1 plus x e to the I eta. To get the imaginary part, multiply upstairs and downstairs by 1 plus x e to the minus I eta. So this is the complex conjugate of that. In the numerator, x e to the I eta times x e to the minus I eta, that's x squared, a real quantity. From the numerator, the imaginary part is x sine eta. In the denominator, we have x squared plus 1, then we have x times e to the I eta plus e to the minus I eta. This bracket is 2 cosine eta. Before using this result, split the integral into 2 integrals. The second integral here is written with the dummy variable of integration y. Do the change of variables, y equal to 1 over x. When x is 1, y is 1. When x tends to infinity, y tends to 0 from above. dy is equal to minus dx over x squared. We can use this minus sign to get the limits of integration from 0 to 1. We have dx over x squared. Y to the alpha becomes x to the minus alpha. Downstairs we get x to the minus 2 plus 2 cosine eta x to the minus 1 plus 1. If we multiply by x squared, we get x squared plus 2 cosine eta x plus 1. So the difference between the two integrals is that here we have x to the alpha, there we have x to the minus alpha. Combine the two integrals. Now we make use of our result. 1 over x squared plus 2 cosine eta x plus 1 is equal to 1 over x sine eta. Summation n from 1 to infinity, minus 1 to the n plus 1, x to the n sine n eta. Let's integrate term by term. Here is the sum. These are the terms that do not depend on x. We have x to the n times x to the alpha over x plus x to the n x to the minus alpha over x. Integrating, we get 1 over n plus alpha plus 1 over n minus alpha. These are guaranteed to be strictly positive so long as the absolute value of alpha is strictly less than 1. This bracket can be written as n squared minus alpha squared. In the numerator, we have 2n. We can take this 2 outside. We can use a minus 1 from here to make the denominator equal to alpha squared minus n squared. Sine eta can also be taken outside. Our integral, 0 to infinity, x to the alpha divided by x squared plus 2x cosine eta plus 1 is equal to this series, which, as we will see, is proportional to sine of alpha eta. Suppose that on the interval from minus pi to pi, we have the function e to the I alpha eta, and then it is periodized so that we get a 2 pi periodic function. The complex Fourier series is summation over integer n, cn. This is the Fourier series coefficient, e to the I n eta. The coefficient cn is 1 over the period, 1 over 2 pi. Then we have an integration over a period. Let's take it here from minus pi to pi. Then we have the function e to the I alpha eta multiplied by e to the minus I n eta. This integral is equal to sinc alpha minus n. The sinc function is defined as follows. Sinc y is sine by y over by y if y is not equal to 0. Sinc y is equal to 1 if y is equal to 0. The complex Fourier series tells us that when eta is between minus pi and pi, e to the I alpha eta is equal to summation over integer n sinc alpha minus n e to the I n eta. Take the imaginary part of both sides. On the left hand side we get sine alpha eta. On the right hand side this complex exponential becomes sine n eta. If n is equal to 0, we have 0. We can take this sum and split it into a sum from 1 to infinity plus a summation m from minus infinity to minus 1 sinc of alpha minus m sine m eta. Do the substitution, m equal to minus n. We get summation n from 1 to infinity sinc alpha plus n sine minus n eta, which is minus sine n eta. The right hand side can be written as summation n from 1 to infinity sinc alpha minus n minus sinc alpha plus n. This bracket is multiplied by sine n eta. Note that sine by alpha plus or minus by n is equal to sine by alpha cosine by n, and cosine by n is minus 1 to the power n. When we combine these two guys, we get minus 1 to the power n. We get sine by alpha, which can be taken outside. There is a by here downstairs. We also get 2n divided by alpha squared minus n squared. This sine n eta is here. Summation n from 1 to infinity minus 1 to the n sine n eta times n over alpha squared minus n squared is equal to pi sine alpha eta divided by 2 sine alpha pi. Go back to our integral. We have 2 over sine eta, and we have this sum here, exactly like this one. The integral is equal to this quantity multiplied by 2 over sine eta. This is the result of our integration. The problematic cases of alpha equal to 0 or eta equal to 0 can be handled using a limit argument. This is the result from the first page. Replace that by n. We can write down the factorial of 3n as gamma 3n plus 1, which is 3n gamma of 3n. We get 1 over 2 pi, 3n, 3 to the minus half plus 3n, then 3 gamma functions with arguments n, n plus 1/3, and n plus 2/3. This 3 can be combined with this 3. We get 3 to the 1/2 plus 3n. In the binomial coefficient, we have n factorial, 2n factorial in the denominator. We divide by gamma of n plus 1, gamma of 2n plus 1. Note that n times gamma n is gamma n plus 1, so these terms go away. We are left with 1 over 2 pi, 3 to the 1/2 plus 3n. Then we have gamma of n plus 1/3, gamma of n plus 2/3. The sum of the arguments is 2n plus 1. Downstairs, we have gamma of 2n plus 1. So what we have here is exactly beta of n plus 2/3 and n plus 1/3. We know that beta of Z1, Z2 is gamma of Z1, gamma of Z2 divided by gamma of Z1 plus Z2. We make use of this result here to write down this sum, this generating function, using the beta function. This term here can be written as the square root of 3, 27 to the power n. Here is the square root of 3. This term with x to the n can be written as 27x all to the power n. Then we have the beta function. Let's use the integral representation of the beta function. Beta of Z1, Z2 is 2 integral t from 0 to pi over 2 sine t raised to the power 2z1 minus 1 cosine t raised to the power 2z2 minus 1. So here sine is raised to the power 2n plus 4 over 3 minus 1. That's 2n plus 1/3. Cosine is raised to the power 2n plus 2/3 minus 1. That's 2n minus 1/3. Swap the order of integration and summation. We have sum n from 0 to infinity, 27x sine square t cosine square t. All those guys multiplied together are raised to the power n. This is the ratio of a geometric series. We need the magnitude to be strictly less than 1 for convergence. Note that the maximum possible value of sine square t cosine square t is 1 over 4. This is because sine square t cosine square t is 1/4 sine 2t squared. This sine has a maximum value of 1, so this product has a maximum value of 1/4. For convergence, we want the absolute value of 27x times 1/4 to be strictly less than 1. Our result is valid so long as the absolute value of x is strictly less than 4 over 27. The geometric series gives us 1 over 1 minus 27x sine t squared cosine t squared. We use the substitution z equal to tan t. If t is 0, z is 0. If t tends to pi over 2, z tends to infinity. T is equal to tan inverse z. dt is dz over 1 plus z squared. If z is equal to tan t, then sine t is z over the square root of 1 plus z squared. Cosine t is 1 over the square root of 1 plus z squared. We write down everything in terms of the new variable z. Multiply upstairs and downstairs by 1 plus z squared. When we multiply this denominator by 1 plus z squared all squared, we get 1 plus z squared all squared minus 27x z squared. In the numerator, we have z to the 1/3 times 1 plus z squared. The denominator can be written as this product using the difference between two squares. Note that this quantity here can be written as 1/2, 1 over z squared minus the square root of 27x, z plus 1, plus 1 over z squared plus the square root of 27x, z plus 1. If we combine these two guys in the numerator, those go away and we get 2z squared plus 2 divided by 2, we get the numerator here. After doing partial fractions, split the integral into two integrals. Compare these with the integral that we have on the second page. Alpha should be between -1 and 1. Here alpha is equal to 1/3. This is okay. We can also obtain what eta is for each integral. Don't forget that x is less than 4 over 27. This integral is equal to pi sine alpha eta over sine pi alpha sine eta. Alpha is 1/3. Sine pi over 3 is square root 3 over 2. Every pi goes away. Alpha is 1/3 and eta is an inverse cosine function. To make our final result look nicer, we make use of four results. The first is that sine cosine inverse u is the square root of 1 minus u squared. This is the square root of 1 minus 27x over 4. This is also the square root of 1 minus 27x over 4. The second result, sine theta plus phi is equal to double sine theta minus phi divided by 2, cosine theta plus phi divided by 2. The sum of these two sine functions can be written as double the product of sine, the sum of these terms divided by 2, times cosine, the difference divided by 2. The third result is that cosine inverse u plus cosine inverse minus u is equal to pi. This means that what we have here is sine pi over 6, which is 1/2. We can also use this result to write down this inverse cosine as pi minus cosine inverse the square root of 27x over 4. The argument of the cosine is pi minus 2 cosine inverse the square root of 27x over 4, all divided by 6. The fourth result is cosine inverse u plus sine inverse u is equal to pi over 2. 2 cosine inverse u plus 2 sine inverse u is equal to pi. Pi minus 2 cosine inverse is 2 times sine inverse. So this cosine here is cosine 1 over 6, 2 sine inverse the square root of 27x divided by 4. Our final result is that summation n from 0 to infinity, 3n choose n x to the n, is equal to cosine 1/3 the inverse sine of square root 27x over 4 over the square root of 1 minus 27x over 4.